our next speaker is Professor Mei Nagappan. So Professor Mei Nagappan is Associate Professor at the University of Waterloo. He received the Outstanding Early Career Computer Science Researcher Award by CSCAN InfoCan in 2020. He received the Early Career Achievement Award from MSR. And he has many distinguished paper and best paper awards. So today he will share his talk about security and runtime performance of code generated by GitHub Copilot. Okay, you have the floor.
Okay, thank you. Thank you, Ian. And thank you for having me here. This is some work that we've been doing over the last couple of years in collaboration with Ashokan, a security researcher in Waterloo, and Samer, who's a systems professor in Waterloo. And the bulk of the work was done by our students, Overa, Daniel, and Harsha. And we wanted to look at these code generation tools, and particularly Copilot, which is one of the most production-ready tools. And as Foots kind of said, several companies are starting to use this already, right? So we wanted to look at the code written by developers using these tools. I first want to kind of acknowledge that Waterloo and is on the traditional land of the neutral Anishinaabe and Haudenosaunee people, and that's where I live and work as well. Let me start with this question. There was this newspaper article that came out about a year or so ago that said, a lot of newspaper articles about this report from Goldman Sachs, which said about 300 million jobs could be impacted by generative AI. And could software be one of them, right? So my question to ask is, can generative AI and these kind of code generation tools automate away programming jobs? And as Romain said yesterday, if there's actually ever a question on a paper, the answer is always no, right? So we'll kind of see if that is actually the case. And I'm going to answer this from the perspective of security and runtime performance of the code generated by humans using Copilot, right? So first we'll go with the security of the code. So does Copilot produce secure code, right? And we did two kinds of evaluation. The first evaluation was a pure mining software repositories kind of work. It was a data set driven evaluation, much like a lot of the research in this area, where you take a prompt, you give the prompt to a code generation tool, you see the output of that prompt, and then you see how good or bad the code is. And then from that result, we kind of understood that it was incomplete and that we had to actually give these tools to users and check what they're doing with these tools and how the code generated from these tools end up. I'll first talk a little bit about the data set driven study. So we took the big wall data set, we took a bunch of vulnerabilities, and we recreated those scenarios. So we kind of rewinded the code base. We went to the commit just before the vulnerability was fixed. We gave everything till the vulnerable line of code in a particular file, and we asked Copilot to generate the next piece of code. And the next piece of code could either be the vulnerable piece of code, which is category A, the fixed piece of code, which is category B, or something else completely, which is neither A or B, right? And then we also fixed a little bit of this and kind of made small changes to the code just to make sure that it was not just syntax problems, and then recategorized them as well. So what did we find? We actually found that Copilot is actually not as bad as human developers in introducing a vulnerability. So about 33% of the time, 1/3 of the times, Copilot produced the vulnerable piece of code like humans. But about 25% of the time, as you can see, Copilot actually produced the fix and not the vulnerable piece of code. Now, there is a possibility that there's leakage in that it memorized some piece of code, but there are some studies that indicate that it memorizes only about 1% of the code that it trained on. So 25% is kind of huge when it comes to that, right? So we find that it is actually producing the fix. And about 40% of the time, it generates something else completely, which humans then have to make it a fix or the vulnerable piece of code, right? And we also found that it is likely to generate non-vulnerable code when it comes to newer vulnerabilities. So you can see that category B keeps increasing for newer code. So 2019 code, it had a higher rate of fix than 2017 code. So maybe it's forgetting some of the older data and does not know that, and it's actually remembering more of the newer data and providing fixes for that, right? And then we found that it actually performs better against vulnerability with simpler fixes. So as you can see, CWE 119 is, and 190 is like very good. These are like integer overflow and things like that, where it's a simpler fix. Whereas something like input validation, which is CWE 20, it actually does very poorly. It always gives the vulnerable piece of code. So when it comes to more complex vulnerabilities, when it comes to semantic vulnerabilities, it's actually quite bad. Right. Then we followed it up with the user study. In the user study, we kind of recruit some participants. We give them programming problems, and we do like a within subject study where we give them a control problem with Copilot and then a problem without Copilot, and then we switch it around for other participants. We record those sessions, and then we manually analyze the videos and the solutions that they generated to understand the code that was produced with it. So instead of just doing some static analysis, we actually did manual analysis on the code. And as for the problems, one of the things that we did compared to previous studies was we started giving more realistic problems that developers might be building on, rather than just saying, build a linked list or how to sort an algorithm or something like that, right? Those are good problems, but they have limited scope as well. So we picked problems that potentially had vulnerable solutions, right? If you ask it for a sorting problem, the probability of having a vulnerability in a sorting algorithm is very, very low, right? We also chose problems where we could manually analyze the solution. So we had domain expertise in those domains. We wanted it to resemble some kind of real-world applications. And finally, it had to be solved within an hour, right? Because we were paying participants to do the study, so we wanted this to be solved within an hour. So we chose two problems. The first problem was a sign-in function for an application given a username and password. And then we also had a problem where they implement a series of transactions between several customers. So what did we notice? For the first sign-in problem, we didn't notice actually a difference between users who used Copilot and users who didn't use Copilot. They produced more or less the same level of secure code. They had similar number of vulnerabilities in their code and similar amount of safe code. But whereas in the transactions problem, which is a slightly more difficult problem than the sign-in problem, we found that users who used Copilot produced more secure code than users who did not use Copilot, right? Statistically significantly more, right? So we also then looked at whether these vulnerabilities in certain vulnerabilities are more susceptible to this, right? When humans are using it, as opposed to our previous study where we found that Copilot was generating more secure code for simpler vulnerabilities and less secure code for more complicated vulnerabilities. When humans were actually using it, we did not actually see any sign of difference between using Copilot or not. They were making similar amounts of mistakes, right? So it was not actually writing any more insecure code for any particular type of vulnerability, right? So the takeaways from our study here is that Copilot is not as bad as humans when introducing vulnerabilities in code. And its performance, in some cases, do differ on types of vulnerabilities, and when humans are using it, not really. And they could be much more useful when users are building more challenging problems than when they're building simple problems. So I think in future studies, we need to start looking at the use of Copilot in real-world use cases and how they work with humans. The next study is on the performance of the runtime performance of the code produced with GitHub Copilot. This was the study done with Daniel, Harsha, and Samer. And in this, we chose a problem that our criteria for choosing the problem was that there should be difference in performance when different users kind of write, and it should again be solvable within 30 minutes, each of these problems. So we chose a IO-intensive problem where if you actually write good code, it'll have faster runtime performance. And then we also did a multi-threaded application, which will again have an impact if you write poor code. So these are problems A and B. So we then did like a within subjects design, and we counterbalanced to do the order effects. We kind of switched the A and B. So we had these 4 kind of cases. And so we had 32 participants with 8 of them doing each of these treatments, right? And what did we notice first? One thing we noticed is that using Copilot actually influenced correctness. We found that when users did use Copilot, they created functionally correct code. When users did not use Copilot, they had a higher chance of making mistakes. They thought they submitted correct code, but they were actually making more mistakes, right? There was even some programs that at the end, I think it was a function of at the end of the 30 minutes, it didn't even compile, right? Like it didn't build. It compiled in the short run, but when built with other libraries, it did not actually build. So we do notice that correctness is a factor, but when it comes to performance, we found that when they use Copilot, the runtime performance of the code is anywhere between 15 to 30% slower. So they got functionally correct code, but their runtime performance was much slower than people who didn't use Copilot. And one caveat here is that we did not ask them to write performant code. We just gave them the problem and said, write code, right? And humans just naturally were writing code that runs faster. And all this code was readable. This was not like code that was tuned for performance, where to the point where performance is great, but you can't actually read or understand this code. Rather, this was code that they expected other humans to read, and it was readable, but it did produce code that was about 30% faster on average. There was one systems developer who was like an extreme runtime performance-oriented guy who had like 10x improvement over the other users. But even that developer, when given Copilot, wrote slower code. Right? They started accepting suggestions from Copilot, and they wrote slower code. So our takeaways from that is that Copilot is better than humans at writing functionally correct code, but they need to be careful when it comes to runtime performance of the code generated with Copilot. So kind of I'll jump back to my question, can generative AI automate away software engineering jobs? With our studies, and as it stands today, I think the answer is no, but they're still very useful when they're used as assistants, right? So I think a lot more studies should try to use Copilot or these generative AI as assistants, like how they were actually intended to be, rather than completely automated sets of tools where everything is just automated and you give it an input and you expect something, an output from it, and it just works. So that's my talk.